trig identities. We were just doing trig identities that were acting on a single variable, so a single angle. There are often times when we have trig identities of either multiple angles or a multiple of an angle. And in this segment, we're going to look at finding trig identities when the trig function is acting on an addition or a subtraction of two angles, and then take that and kind of extend it on to how that applies to the cofunction identities. Now, first up, we're looking at sum and difference identities, and then we'll go to the cofunction identities. So here, notice that the sign of the parentheses, so this is the angle sum that the sine function is acting on, and it's an angle alpha plus another angle beta. Now, if I had the values for alpha and beta, and they were fairly easy to work with, that their addition came out to be one of our special angles, or if I only wanted an approximation, certainly I would follow order of operations and add the two angles together and then take the sine of that sum. But what if one's a numerical value and the other one's a variable, but I need to get it replaced with an equivalent expression that would allow me having trig functions just acting on a single angle? Or maybe I have where they're both variables, but I need to have it rewritten where I have an expression that's equivalent to it, where the sine and cosine functions or the trig functions are individually just acting on their own single angles. Well, the thing that you have to be very careful about, and one of the things that's a very common mistake for students in trig when they're first starting out to make, is that there is no distributive property for the trig functions. That idea of the distributive property is distribution of multiplication over addition or subtraction. It does not apply to functions in general. So when I see the sine of alpha plus beta, it's not equivalent to the sine of alpha plus the sine of beta. That does not give you the same expression. What it is equivalent to is the sine of alpha times the cosine of beta plus the cosine of alpha times the sine of beta. So there's an expansion you have to do to make the left side come out the same as the right side. And I have comparable expressions for the sine of a difference of two angles, the cosine of a sum of two angles, the cosine of a difference two angles, the tangent of the sum of two angles, and the tangent of the difference two angles. And if you wanted to get it for the other three trig functions, the cosecant of the sum of two angles, the cosecant of the difference of two angles, etc., then you could just do the reciprocal relationships between the trig functions and get those. But for this segment, we're just going to be looking at the ones that are listed here. Now notice the sine of the sum of two angles and the sine of the difference of two angles, sum when it's added, difference when it's subtracted, are very, very similar to each other. In fact, the only place that they differ is depending on whether it's a plus between or a minus between. So a memory device that I like to use is that when you're doing the sine, S-I-N, of the sum of two angles or the difference of two angles, the plus or minus matches in what they had with between the two angles to what you have with between the two expressions, but the trig functions within the terms don't match. So this is sine alpha cosine beta, see they're different trig functions, and then cosine alpha sine beta. And also, just whichever trig function is started here with that first angle, that's the way that first term starts, and then go to the different trig function and the different angle, and to fill it out. So when you're doing the sine of the sum of two angles or the difference of two angle, the sines, S-I-G-N's, match, but within the terms of it, the trig functions don't. Now let's look at the cosine of the sum or difference of two angles. So the cosine of alpha plus beta is cosine alpha cosine beta minus sine alpha sine beta. And then the cosine of alpha minus beta is cosine alpha cosine beta plus sine alpha sine beta. So for the cosine of the sum or two angles expression expansion that's equivalent to the original, the trig functions match within the terms, but the plus or minuses don't between the terms and between the angles. So it kind of just gives me, again, a memory device for it. And also look that within each of the terms, the angles, you take the one angle first and then the other angle second. Now, what I did for the tangent of the sum or difference of two angles is I rewrote it, or I wrote it as a combination so that you follow the path, so that I condensed, instead of having two different lines for it, I condensed it in a single line. So the tangent of alpha plus beta, that's the top part of it, so you're going to follow all the top signs for it. So it's the tangent of alpha plus the tangent of beta, divide by 1 minus the tangent of alpha times the tangent of beta. And for the expansion of the tangent of alpha minus beta, it's the tangent of alpha minus the tangent of beta over 1 plus the tangent of alpha tangent of beta. Now that we've kind of looked at the structure of these expansions, let's see how we can use those in an example. So it says to find the exact value of. So this means you can't go to decimal approximations. If there's radicals in the answer, you have to leave the radicals in the answer. And you always want to simplify. So here it's the cosine of, here's my parentheses of what the cosine is acting on, and between these two angles there's a minus. So we call that the cosine of the difference of two angles. So then I look and see cosine and difference between. This is the expansion that I need to use. So think of cosine, and then alpha is your first angle, beta is your second angle. So I'm going to go cosine of 5 pi over 6 times the cosine of pi over 4, and then plus sine of 5 pi over 6 times the sine of pi over 4. So this second expression expansion that I wrote is equivalent to the original. So next up, within each of these are trig functions of our special angles, the ones that we've been working on for several different videos to be able to find their value. So the cosine of 5 pi over 6, we'll think 5 pi over 6 is a second quadrant angle. So the cosine is the same plus or minusness of the x coordinate, and to get to the second quadrant I have to go left, so it'll be a negative. And the cosine of the over 6's, that's the square root of 3 over 2. So this will be negative the square root of 3 over 2. And you can kind of refer to your unit circle, or you can refer to the work that was done in the special angle, trig functions of special angles. Now how about the cosine of pi over 4? Well, pi over 4 is a first quadrant angle, and the cosine of an over 4 angle in radians is square root of 2 over 2. Then bring down the plus. Sine of 5 pi over 6. Well, 5 pi over 6 again is a second quadrant, but sine goes with the y coordinate, and the plus or minusness to get into the second quadrant for the sine function is going to be up, so that's positive. And the sine of a radian measure with the over 6, that's a half. So that's positive a half times, and pi over 4 is a first quadrant angle. Sine is positive in the first quadrant. In fact, all the trig functions are positive in the first quadrant. And then the sine of pi over 4, well, the over 4's for the sine is the square root of 2 over 2. Now, don't forget your order of operations here. You multiply before you do the addition. So negative square root of 3 multiplied to the square root of 2. When you're multiplying radicals, you multiply the outs to outs and the ins to ins, and then they stay in. So the square root of 3 times the square root of 2 is the square root of 6. So I have negative the square root of 6 over 2 times 2 is 4, plus 1 times the square root of 2 is the square root of 2 over 2 times 2 is 4. And now I have common denominators, so I can write this addition over that common denominator. So it's negative the square root of 6 plus the square root of 2. all over 4. And if you remember back to radicals, I have to have like radicals to condense them any better with addition or subtraction. And square root of 6 doesn't simplify any further. And it's a different radicand than square root of 2, which doesn't simplify any further. So the best I can do is to write that as negative the square root of 6 plus the square root of 2 all over 4. Let's do part B. So here, if I were to try to add 210 degrees plus 45 degrees, I would get 255 degrees, which is not one of our nice angles, our special angles. So what I want to do is to look at the tangent of the addition of two angles, expansion. So the tangent of the addition of two angles, expansion, I have tangent of alpha, and remember that's alpha, that's beta. So tangent of 210 degrees plus the tangent of 45 degrees divide by 1 minus the tangent of 210 degrees times the tangent of 45 degrees. So now 210 degrees, that is a third quadrant angle. Remember, tangent is y over x. And so if I take a negative divided by a negative, I have an overall positive ratio. So tangent is positive in the third quadrant. Now the reference angle for 210 degrees is 30 degrees. So remember, it's to the nearest x-axis. So I take 210, subtract the 180, that's a 30-degree reference angle. So with the 30 degrees, the sine function is half, and the cosine function of a 30-degree angle is the square root of 3 over 2. So when I take a half and divide by the square root of 3 over 2, and I flip and multiply, the 2's will cancel, and I'll have 1 over the square root of 3. Rationalizing it, I get the square root of 3 over 3. And again, in a third quadrant, that's going to be positive the square root of 3 over 3. So I was giving you the sine and cosine of the reference angle. If I did it of the 210 degrees, it would actually be negative a half in the numerator, and then negative square root of 3 over 2 in the denominator, and negative divided by negative is a positive. So I'd still get this. Plus the tangent of 45 degrees. Well, the tangent of 45 degrees is 1. Divide by 1 minus, I have tangent of 210 we already saw was the square root of 3 over 3, and tangent of 45 is 1. So now this fraction is a complex fraction because it has fractions in the numerator and or the denominator. This last term in the denominator is the square root of 3 over 3 times 1, so that's just the square root of 3 over 3. And I want to get it where I don't have these fractions in fractions. So I look at the denominators within the numerator and the denominator, and they're both 3's. So I can build this overall fraction, top and bottom, by 3, because 3 over 3 is just multiplying by the number of 1. So I'm not changing the value of it at all. I'm just changing the way it looks cosmetically. Now 3 times the square root of 3 over 3, the 3's will cancel, and that'll give me the square root of 3. Then 3 times 1 is plus 3, divided by 3 times 1 is 3, minus 3 times the square root of 3 over 3 times 1 just gives me the square root of 3. So that exact value is the square root of 3 plus 3 divided by 3 minus the square root of 3. Now that doesn't simplify any further either. The only way I can remove common factors from the top and the bottom is if they're attached as common factors, multiplication. These are attached by plus or minus, they're terms, and you can't cancel out terms between the numerator and the denominator of a fraction. And then also, these aren't opposites completely of each other because the 3's have the same sign. It's only the square root of 3's that have opposite in sign. So that is as far as that expression can be simplified that way. We can rationalize it To rationalize it, you would multiply the top and the bottom by 3 plus the square root of 3, the conjugate of that denominator. So that's how you would finish out with rationalizing it. So next up, we're going to do some more examples of applying these identities of the sum and difference. So what I'm going to do is take a moment to rewrite these all in the condensed form and to do some more examples. Okay, so I've rewritten these first couple trig identities of sum or difference of two angles, so they're more condensed and giving us more room to work out the problems. And then this type of a question kind of connects with what we did before when we were given an trig ratio of an angle and what quadrant it was in, and then how to find the remaining trig ratios of that. We're only going to look for the ones that we need within the expansions. And so I have the cosine of alpha being 5/13 with alpha being in quadrant 4. But then I also have a trig ratio of the other angle beta and where beta is. So we are going to need to use that information to get the remaining trig functions that we need for these expansions as we go through. So the first one is the cosine of alpha minus beta. I don't know alpha and beta, so I can't do the order of operations and subtract them. So the best I can do is do the expansion. So the cosine of alpha minus beta, remember for cosine, the trig functions match, but the sine doesn't. So the SIGN. So it'll be cosine alpha, cosine beta, plus sine alpha, sine beta. And also, this starts always with the trig function you're working with and that first angle, and then you kind of switch it out after that. Now, I want to find the cosine of alpha and replace it with what its ratio is. And I look, and that was actually given to me. The cosine of alpha is 5/13, so I can actually take the cosine of alpha out and put 5/13 in. And this is multiplied, but now I need the cosine of beta. And I don't have the cosine of beta to start with. I have the tangent of beta. So what we're going to do is write those over here so that we can refer to them. Starting out, let's do for alpha. So alpha is in quadrant 4. So I have a quadrant 4 angle. Always go to the nearest x-axis. The cosine ratio is our x over r. So r is 13, that's the hypotenuse. And the x-coordinate is the horizontal run. And to find the y-coordinate, I'm going to use the Pythagorean theorem and then realize that I'm going down, so I need to use a negative on it. So 5 squared plus y squared is equal to 13 squared. So that's 25 plus y squared is equal to 169. Subtract 25y squared is equal to 144. Take the square root. Y is either plus or minus 12, but it has to be minus 12 to get down into the fourth quadrant. Okay, then let's do this also for beta. Beta is in quadrant 2. So we're going to go into quadrant 2, go down to the nearest x-axis. This is beta, and that was alpha. All right, now we have the tangent of beta in quadrant 2 is negative 3/4. Now remember, that minus sign might float between in front of the fraction or in the numerator or in the denominator, but when I put it on my figure, I have to go along with the sign that the variables need to get into the quadrant they're supposed to be into. So the quadrant 2, you have to go left and up. So since you have to go left and up, the x-coordinate has to be negative and the y-coordinate has to be positive. So when I'm looking at this, I know it says negative 3/4, and by the definition of the tangent of an angle's ratio, it's y over x, but I need to get into the second quadrant, so this is really a 3 over a negative 4. But remember, positive divided by negative is negative, negative divided by positive is negative. So these are an equivalent expression. It's just this one is like the general value of it, and this one actually has the sign where it needs to be for what quadrant that angle lands in. So my work with this, my y is 3, and my x is negative 4. And when I use the Pythagorean theorem, I get my hypotenuse is 5. Remember, your r is always positive. Okay, so now when we're looking at this, our reference angle is to the nearest x-axis, so that's our reference angle. So cosine of beta, look at beta's picture. Take the cosine of this angle. The cosine of this angle is adjacent over hypotenuse. So that is a negative 4/5. Then plus the sine of alpha. Alpha, go to alpha's picture. The sine is opposite over hypotenuse. So that's a negative 12/13. And then sine of beta, we're going to go to this figure, and the sine of this is opposite over hypotenuse, so that's 3/5. Now follow your order of operations. We have negative 20 over 65, and then plus a negative 36 over 65. So then negative 20 over 65 plus negative 36 over 65 is a negative 56 over 65. And if I could simplify that fraction, I would, but there's no common factors between my 56 and my 65. Okay, so now let's look at the next one. Sine of alpha plus beta. That's sine, so the plus or minuses match, but the trig functions don't. So plus following the top path. So that's sine alpha cosine beta, and then plus cosine alpha sine beta. So my sine alpha, once I have the triangles drawn for the angles, then I've got them to refer to throughout that problem. So sine of alpha, here is alpha. The sine of it is opposite over hypotenuse. So negative 12/13 times cosine beta. Go to beta's picture. The cosine is adjacent over hypotenuse, negative 4/5, plus cosine alpha. Go to my alpha picture. The cosine is adjacent over hypotenuse, 5/13. And then that's times sine beta. Go to your beta picture. The sine is opposite over hypotenuse, so 3/5. So I have negative times negative is positive. Positive 48/65 plus 15/65. So 48 plus 15 gives me 63/65. Okay, next up, and the last one we have here is the tangent of alpha minus beta. So the tangent of the minus one, you're going to follow the bottom path. So the tangent of alpha minus beta is tangent alpha minus tangent beta divided by 1 plus tangent alpha times tangent beta. Tangent of alpha is opposite over adjacent, so negative 12/5 minus tangent of beta is negative 3/4 over 1 plus tangent of alpha is negative 12/5 times tangent of beta, which is negative 3/4. So I have negative 12/5 plus 3/4 over 1 plus a positive 36/20. Now again, I have a complex fraction. It's got fractions and fractions. So I want to simplify this. Look at all your denominators in the little fractions. There's a 5, there's a 4, there's a 20. The lowest common denominator is 20. So we're going to multiply the top of the fraction and the bottom of the fraction by each by 20, and 20 over 20 is just multiplying by 1. So I'm not changing the value of it, just the way it looks cosmetically. So when I take 20 times negative 12/5, 5 goes into 20 4 times. 4 times negative 12 is negative 48. When I take 20 times 3/4, 4 goes into 25 times, and 5 times 3 is 15. When I take 20 times 1, it's 20. And when I take 20 times 36 over 20, I get 36. So combining my terms in the numerator and denominator, negative 48 plus 15 is a negative 33 over 20 plus 36 is 56. So here I get my negative 33 over 56 for that answer. So hopefully you'll see how you need to really, this is all a whole process of training your eyes to see these expressions as the factors that they are, how you make the replacements, what the values are actually representing. So we're going to do one more set of examples with this, which will hit home our cofunction identities. So now let's go ahead and do the same process we've been doing on all the other examples, but with these expressions, the cosine of 90 degrees minus alpha, and then another example, the sine of 90 degrees minus alpha, and then tangent of 90 degrees minus alpha. So I do have two different angles. One of the angles is 90 degrees and the other one is alpha. They're attached with a minus between, so it's a difference of two angles that I'm taking the tangent, the sine, or the cosine of. So I can do my expansions with the difference of two angle formulas for it. And then because it's 90 degrees minus alpha, or if you had it in radians and it was pi over 2 minus alpha, you're talking about an angle alpha, and then 90 degrees minus alpha is the complement of that angle alpha. So let's look here at our expansion. So the cosine of 90 degrees minus alpha, it's the cosine of a subtraction of two angles. So I come to cosine and follow the bottom path because it's subtraction. So this is going to be my cosine of what's the first angle in your expression. So here that's 90 degrees times the cosine of the second angle in the expression. Here that's alpha. And then remember, minus is going to be the bottom path, so we're going to do a plus. Sine 90 degrees sine alpha. From the sine of the first angle times the sine of the second angle. Now, if there is a specific numerical value for your angle, and it's a special angle, you can make the replacement from what you know from the unit circle or even from the other applications that we did. So the cosine of 90 degrees. Well, the cosine of 90 degrees, I know what that is. That's 0. Cosine of alpha, alpha is a variable angle, so I just have to write cosine alpha. Plus, the sine of 90 degrees, I know what that is. The sine of 90 degrees is 1 times the sine of alpha. So 0 times anything is 0. So I have 0 plus 1 times sine alpha is sine alpha. So I get 0 plus sine alpha is just sine alpha. So we call this the cosine. The cosine is the cofunction of sine because the sine of an angle is the same as the cosine of that angle's complement. So now I know that if I ever have the cosine of 90 degrees minus alpha, or remember pi over 2 minus alpha, I can make a replacement that's the same as the sine of alpha. So that's a cofunction identity. Let's do the next one. Sine of a subtraction of two angles. I'm going to do the bottom path. So it's the sine of the first angle times here the trig functions don't match. So this is going to be the cosine of the second angle. So cosine of alpha, but the plus minuses match. That's still going to be minus here. Minus the cosine of the first angle, so cosine of 90 degrees times the sine of alpha. Well, sine of 90 degrees is 1. So I have 1 times the cosine of alpha minus cosine of 90 degrees is 0. 0 times sine alpha. So I have cosine alpha plus 0, which is cosine alpha. So another cofunction identity is that the sine of 90 degrees minus alpha can be replaced with cosine alpha, and they'll be the same thing. They're equivalent. That's an identity. Lastly, we have the tangent of 90 degrees minus alpha. So let's go to the tangent of 90 degrees minus alpha. We're actually going to utilize the information that we've already gained from part A and part B to do part C. The tangent of an angle, even if it's an expression that's your angle, is the sine of that angle divided by the cosine of that angle. That's from your one of your 8 fundamental trig identities. So we're going to look at this as the sine of 90 degrees minus alpha divided by the cosine of 90 degrees minus alpha. Same angle, sine of it over cosine of it for the replacement for tangent. But I just saw that the sine of 90 degrees minus alpha is the same as the cosine of alpha. So I can take this numerator and replace it with the cosine of alpha. The cosine of 90 degrees minus alpha is the same as the sine of alpha. And if I have the cosine of alpha divided by the sine of alpha, that's the cotangent of alpha. So we get that the tangent of 90 degrees minus alpha is equal to the cotangent of alpha. Again, those cofunctions are telling you that you have the trig functions of the cofunctions will be equivalent of the complementary angle. So hopefully this has been helpful in order to help you get to where you can make replacements of trig functions acting on additions of two angles, subtraction of two angles, or your cofunction ideas. And again, if you wanted the sums or differences for the cosecant of the sum of two angles, the difference of two angles, the secant of the sum of two angles, or the difference of two angles, or the cotangent of the sum of two angles or difference of two angles, you would just have 1 over these expressions for it and can do your replacements that way.